Hello students, this lesson is on graphing and analyzing the exponential functions through the lens of transformations of functions. Alright, so let's take a look. So just a word of caution, okay, as we're going through this lesson and future lessons on the subject of exponential functions, please do not forget our goal leading up to the beginning of the last lesson, which was trying to figure out how to solve a problem like this, okay? And as I've alluded to in the previous video, okay, this is, in order for us to solve this exponential equation, we need to understand the inverse of an exponential function, which is what we're trying to get at here, okay? So we need to understand the exponential function so that we can understand its inverse, okay? So in that pursuit, okay, an inverse to an exponential function is needed because we are trying to find the x values that causes the exponential function to generate those y coordinate of 5. So let us continue studying this exponential function of the form f of x is equal to a times b to the rx, okay, so that we can eventually understand its inverse. All right, so remember concepts of transformations of functions, right? F of x minus h plus k, where h and k just causes a horizontal and vertical shift. So those concepts are still very much applicable, even when we're dealing with exponential function. As a matter of fact, it's applicable for universally any function. So this format that I have here with the exponential function that we've been working on, okay, this is a more generalized way of writing it, okay? And again, it's really no different from what we had discussed in the previous lesson, other than the fact that we are going to be shifting the exponential functions that we're graphing. Shifting and reflecting, that is. Okay. The domain, okay, for such function, just like in the last video, it's all real numbers because we can substitute any value of x and we can still generate some y coordinates out of this. The domain, on the other hand, is slightly different, okay? In the last video I said if the function was simply of this form, then the range is simply y is greater than 0, right? But because we're shifting it, okay, that's going to cause changes in the range, okay? And it's going to be largely dependent on two values, a and k. It's going to be dependent on the value of a and the value of k here. So these two values. So what we're going to try and do in our first problem is we are going to try to sketch this function 3 times 1/2 to the negative 1.5 times x plus 4 plus 2. And we're going to state domain and range. So we're going to attempt this, okay, by analyzing whether or not this is a growth or a decay kind of situation, and then we're going to try and graph this. Now, this, mind you, this is a sketch. We're not graphing individual points. The only point that we'll be graphing is the coordinate that we're familiar with, which is the y-intercept. So if this function were to be re-expressed as 3 to the power of 1/2 negative 1.5x, okay, without the vertical and horizontal shift, I immediately recognize that that would be my y-intercept there. So that coordinate, okay, is going to be the only point that we will be graphing, okay, accurately. Or, I mean, like, just representing, okay? Not even so much accurate. Just representing, okay? And we're going to be applying the vertical and horizontal shift. This value over here, that negative 1.5, okay, even though I'm telling you a specific numerical value for the quantity of r there, there's no need to emphasize shape, differences in shape of the exponential function. The only thing that you need to recognize is how does that number there, in conjunction with the base, cause the overall function to either grow or decay, okay? So what do I mean by that? Well, I know that y equal to 3 to the 1/2 3 times 1/2 to the negative 1.5x. If I rewrite that, that is equivalent to this guy right here. So because of this, okay, I will recognize that this is actually an exponential growth, right? So this graph is going to experience exponential growth with a y-intercept of 0, 3 and a horizontal asymptote of 0. So I'm going to graph that first, okay? And after I have that graph, then I'm going to perform the necessary transformation. So that's the picture right there, and this is the really the only point that I'm graphing with any kind of accuracy. Any other things here, you don't really need to, okay? You just need to have the general shape of the exponential function drawn, okay? All right, the next thing we're going to do is we're going to apply the horizontal and vertical shift. So we're going to be shifting this 4 units to the left and 2 units up. So 0, 3 as a result is going to be moved to negative 4, 5. The horizontal asymptote, which was originally at y = 0, will now be pushed up to y = 2. This is the final graph that we were trying to pursue. Try to observe whether or not there are any patterns or generalizations that we can make as far as recognizing what the domain and range is, right? So right now the domain, okay, is all real, and the range is y is greater than 2. I just set this, so I'm going to fast forward. All right, next we're going to try and graph y = negative 2 times 3 to the negative 0.5 times x minus 4 plus 5. Again, we're going to try to do this in pieces. We're going to graph this piece alone first, right? So 2 times 3 to the negative 0.5x. From our experience in the previous lesson, we will recognize that this is actually going to be an exponential decay because 3 to the negative 0.5x is equivalent to 1 over 3 to the 0.5x. And this guy right here is below 1 but greater than 0. This is going to be an exponential decay. So the overall graph, okay, will have a y-intercept of 2 and we'll have this shape. And notice I even did away with the actual grid itself. I just drew an xy axis and I labeled the point, okay, for where it should be. This is the way of thinking that most math teachers would want you to proceed. Yes, we want you to be accurate, but we also want you to have a general sense of how the function is shaped and how the function is behaved. You do not need to plot individual points because that would defeat the whole purpose of understanding the generalization, right? So we have this graph right now. This is not the final. This is not the final, right? We still need to shift this horizontally and vertically. We're going to move this 4 units to the right and, oh, actually, no. Before we do that, I did not apply this negative. What will that negative do, you may be wondering? We're going to be flipping this over the x-axis. So it's going to look like that. And then we're going to be shifting this 4 units to the right and 5 units up. So 0, negative 2 will end up at 4, positive 3. And the shape of the graph is going to look like this. The vertical asymptote is now at 5. Not vertical, horizontal. What am I saying? The vertical asymptote has been moved to y = 5. So what is the domain and range, you may be wondering? Well, the domain is still all real numbers. And as a matter of fact, it is always all real numbers because we can substitute any value of x inside of an exponential function and it will always be all real. What is the range? Well, in this case here, it's got to be less than 5. All right, so in summary, right? The graphs of exponential function, okay, this is the general form. The domain is always all real numbers. The range depends on values of a and k, whether the function is growing or decaying, whether or not a, right, is positive or negative, as we saw in the previous example here. Here, in this case, y is less than 5. Well, that's because it's dependent on this guy right there, right? If this had been positive, then the graph would have looked very different. The graph would have looked something like, well, it would have been coming from above. It would have been coming like that, in which case then y would be greater than 5, right? So again, it's dependent on the value of a and k. All concepts of transformations of functions, they still apply. So all those things that we learned about transformations of functions in the previous unit, okay, please don't throw that out the window. We need to reapply them here. All exponential functions will pass the vertical and horizontal line test, as we've seen. I did not address this directly, but I'm going to address it now, right? So if you look at this, horizontal line test definitely will pass. Vertical line test definitely will pass, right? This kind of function is, in fact, a one-to-one. So yes, an inverse function for an exponential function, will in fact exist. How are we going to get there? We're going to be talking about that in the next video.